Welcome to this video on Ampere's Law, or more appropriately called the Ampere-Maxwell Law. The form we actually use it in today was devised by James Clerk Maxwell when he was unifying all of electromagnetism, or classical electromagnetism. But we do give some credit to André Marie Ampere because of the foundational work that he laid in the earlier 1800s. Now, what we're going to do in this video, even though we're looking primarily at the Ampere-Maxwell law, is we're going to compare it a lot to Gauss's law, and specifically Gauss's law for electricity, okay, not the magnetism side. And so over here on this side, we'll take a look, and I'm just abbreviating it here, and I'm going to just refer to it as Ampere's law. So let's take a look at why we're going to compare the two. Let's say that I had a rod here of charge. Now, we're going to assume that this rod is very, very long, so we don't have to worry about the fringing. And we're going to think about here that this rod has a positive charge. And we looked at before that if I picked a point over here, and I wanted to know what the electric field was at that point, it was a little bit more complicated than if this were just a single smushed up point charge, because we knew that the electric field due to a point charge was equal to this relationship, 1 over 4 pi epsilon naught times the value of the source charge over the distance you were away squared. Now at this point over here, we obviously said that this is not just one point charge, which is what this equation described. It's actually a whole ton of point charges all added together that are all individually affecting, if you look at it in that form, all individually affecting this point E over here. So really what we ended up having to do then was say that every tiny little dq value that makes up this rod is contributing a dE value amount of the electric field, which then I needed to write in the form like this. Now, additionally, I couldn't just leave it at that point. I had to do so much additional work. I have to obviously integrate both sides. I'm going to have to change my variable of integration here because these things don't really compute, and so on and so forth. And this was going to take a long time, or a lot longer time. Now, I referred to this before in earlier videos as sort of the brute force calculus method. And that is in equivalence here with Ampere's law. That would be looking at the Biot-Savart law, where we had sort of a little bit of a cumbersome equation that we had to use in using a lot of calculus and oftentimes a lot of substitutions that are sometimes hard to remember. But Gauss's law comes along and then says, hey, you want to figure out the electric field at that point? If you have a fairly, symmetrical situation, how about you do this? All of the points along this line and corresponding on this side, all the electric field's the same along all those points. So why don't you make a enclosed imaginary surface, which here I'm using a cylinder, and then you can use the idea of electric flux, and you can say that the surface integral E dot dA is equal to the amount of enclosed charge over epsilon naught. And you could use the surface integral and you could say, well, once I've actually added up all of the surface area here that does in fact have electric flux, we said the top would not and the bottom would not, that this area over here, all right, of the sides is going to be 2 pi r times L, and I could use, some of that to figure out what the electric field is at any point on that surface. So what Gauss's law does is it takes a little bit more of a complex calculus method and it reconverts it into looking for symmetry, looking for surfaces that can be used. Ampere's law is going to do something very similar for us in terms of figuring out the magnetic field around a current carrying object. Okay. Now, a current carrying object, what I mean, usually it's going to be some sort of a wire or a solenoid or a toroid or some shape that is carrying current. Okay, so let's take a look at it for a really long wire. So what I'm going to do here is we're going to make an infinitely long or a very long wire, and let's just say that the current is running up the plane of the screen. So if we use the right hand rule with the curl of our fingers, we can put our thumb in the direction of the current and our fingers would curl around the wire. They would curl into the plane of the screen on this side, and they would come out of the plane of the screen on this side. Now that's great, we know the direction of the field, but what if we wanted to figure out what the value of the magnetic field was, let's say at this point over here? Well, we could use the Biot-Savart law, and we could start setting up the law, and it's a little cumbersome, and we have to use cross products and all sorts of things, and we could do that, and that would be fine. And you can look back at the videos to take a look at how we started to structure that process. But if you want to use a simpler method where there is symmetry or a little bit more simplicity in the shape, we can actually use Ampere's law. And we're going to do something very similar to what we did with Gauss's law. Now what Ampere's law says is that, let's say I pick this point here, that I want to figure out what is the magnetic field at that point. Well, what I can say is that at any point around this current carrying wire that lies on a circle or a line that I enclose here, okay, so it's a continuous line, anywhere along that line I'm going to have the same value of B, okay, magnetic field. So what I'm going to do here is I'm going to say that this has a radius of r, and the radius of r would be the same at all points. Now, the equation for Ampere's law is going to be the integral of B dot dl, we'll talk about what that is in a second, is equal to the current times the vacuum permeability constant. So it looks very similar to Gauss's law in the fact that Gauss's law takes a field times an area vector differential, and it says that that is proportional to the amount of charge that you enclose in that surface over some fundamental constant. We see two very, very similar things here when we look at the two equations. Now let's talk a little bit about what is actually happening in this situation. Well, in this situation, what you're trying to say is that if the magnetic field is constant everywhere on this loop, then I can actually pull that out of the integral, and I can actually only integrate these tiny little current elements along the path. And if I sum up all of those little tiny path values along the entire path around here, what I should end up getting is the circumference of this path, which I know is going to be, if I sum up all these little pieces, I'm going to get 2 pi r, and that we know is equal to I over, or I times mu naught. So if I solve for the magnetic field at that point, I end up getting B is equal to mu naught times I over 2 pi r. And this hopefully rings a bell, and this was that special case of the Biot-Savart law where we were looking at a really long wire and trying to figure out what the magnetic field was at a specific distance away. Now that's a whole lot easier than the entire long-winded process that we went through with the Biot-Savart law. So we can see here that using this idea of symmetry, what the Ampere-Maxwell law says is that current is directly proportional to magnetic field strength at some point around the current carrying wire, and that it is symmetrical at all points around any given space. So I could use this law for many different kinds of situations as long as I can see some sort of symmetry where the path that I draw now, instead of the surface that I draw, that the path that I draw is equidistant to the current carrying wire. And the reason we want it to be equidistant is because we want to draw a surface where in this case, where the electric field is the same everywhere on that surface. Here we want to draw a path or a line that is enclosed where the magnetic field is the same everywhere. And we can then use the geometry of that nice shape in order to calculate the value of the magnetic field, much the same way we did with Gauss's law for electricity. So in the next video, what I'm going to do is take a look at using Ampere-Maxwell law to figure out the value of the magnetic field at different points around a solenoid and some other common shapes of current carrying wires.